Hi, my name is Andrea Robinson, and I will be presenting my research on the analysis of dark scattered neutrons and plastic scintillator detectors. Exotic nuclei near the neutron drip line are often studied using plastic scintillator detectors. As neutrons are emitted, the neutrons scatter off of atoms within the detectors, traditionally leaving enough light to be detected, but also commonly leaving insufficient light to be detected, known as dark scattering. In order to interpret results from data collected using scintillator detectors, simulations are heavily relied on. And previous experiments have highlighted the need to improve these simulations, particularly by increasing our knowledge of dark scattered neutrons. So, one of the goals of this experiment was to measure the angular distribution of dark scattered neutrons using a plastic scintillator array optimized to study dark scattering. Now, looking at the experimental setup, you can see just why this is so good for studying dark scattering. The use of the target detector here provides an unambiguous location of the unrecorded first scatter. And the staircase array configuration provides an improved angular resolution. So some of the things that we know about this setup are the distance from the source to the target detector, the distance from the target to the scattering location, the angle at which a neutron scatters, and the delta T, the time it takes for the neutron to be produced all the way to dark scattering. However, what we don't know is the time it takes to get from the source to the target, the actual first hit. This is important because that's what we use to determine the incoming neutron energy. We traditionally go from time of flight to velocity to energy. However, we don't know this time of flight with a known distance. What we do know is that we can relate velocity of the scattered neutron to the velocity of the beam because there's a unique energy that could scatter to a specific angle within a given delta time window, which we record. So using that knowledge, we can create a relationship between the two, seen in equation 1, and solving that equation for the velocity of the beam, we get equation 2. However, this has two unknowns, so we need another equation. And for that, we look at conservation of momentum. Now, with this, we're assuming that this is a perfectly elastic collision and carbon has infinite mass. And with that, we can use relativistic momentum to create equation 3 and solve that for equation 4. With two equations and two unknowns, we can solve for the velocity of the beam and reproduce figure 3 with a corresponding neutron energy spectrum in figure 4. This is good because we see the gamma peak expected at 30 centimeters per nanosecond and the expected drop off around 800 MeV, which is the upper limit of the energy for our neutron source. Now that we have the energy, we're able to see how the neutron scatters for a given energy and the scattering probability. So this is made up of the angular distribution, which is how many neutrons scatter at a given angle, and the scattering efficiency, which is the likelihood that a neutron scatters to a given angle. Combining that and normalizing over the probability relative to all dark scattered events, we get this preliminary scattering probability. It's still preliminary because we're still looking at ways to adequately remove the background noise such as cosmic muons, but we're still able to create it. It is promising because it agrees with what we've seen before in the previous experiment. However, it adds an improved resolution from 10 degrees to 5 degrees, and also more information on dark scattered events instead of traditionally scattered events. So in conclusion, we're able to reconstruct the time of flight for dark scattered events in order to get the incoming neutron energy, and we're also able to produce this preliminary dark scattering probability. Now, I would just like to acknowledge the NSF and CEU for making this research possible, and also to the collaborators in MONA for helping with the experiment. Thank you.